pass out questionnaires on the lectures, and if you fill these in, apparently you will receive free of charge, courtesy of CERN. How many times do you get things like that? A copy of the transparencies of these lectures. Now, I haven't shown any transparency, so I have no idea what you're going to get, but I'm sure it will be something worthwhile. Okay, today in the fourth and thankfully final lecture in this series, I'm going to talk about dark matter. And originally I said I would talk about dark energy if I could think of anything reasonable to say. I have not thought of anything reasonable to say about dark energy. So today we'll only cover dark matter. So let me remind you of the idea that we've started with and have been coming back to over and over, that the structure that we see in the universe today is the result of the growth of gravitational instability of small initial seed perturbations that were produced in the very early universe, presumably during inflation. So yesterday, we were concerned with the origin of the small initial perturbations. Why isn't this completely smooth? And that was answered by inflation. And today, the topic is the nature of these damn little black dots, right? So the things that appear in the computer as little dots, masses, what is the matter of the universe? What is the nature of matter in the universe? And we know, in fact, that if we look at galaxies and things in the universe, there are missing pieces because, as I will review, the evidence that we have is that most of the mass of the universe is dark. This used to be called missing mass, but in fact, the mass is not missing, it's the light that's missing. So a better name for this phenomenon is dark matter. And what are these missing pieces in our picture of the universe? So let me start with something very basic, and that is the rotation curves of galaxies. So if you go out tonight and look at your telescope at this galaxy, I have no idea which galaxy it is, what you would see, if you look carefully, is that the galaxy is rotating. There are stars in the galaxy and hydrogen atoms, CO molecules that are rotating about the center of the galaxy. And we can take advantage of the measurements of the rotational velocity to deduce a mass for the galaxy. And again, this is a very simple idea, and it's similar to the way we determine the mass of the sun by measuring the rotational velocity of the Earth. The circular acceleration is just set equal to the gravitational acceleration. So by determining the velocity and the distance, we can determine, in this case, the mass of the sun, and we can do the same thing to determine the mass of a galaxy. There will be a star here that is red-shifted, a star here that's blue-shifted. We can determine the rotational velocity and measure this distance to get a measure of the mass of the galaxy. And when we do this, we find evidence for dark matter. And this is an example from the rotation curve of M33. So this is a measure of the velocity of rotation as a function of the distance from the center of the galaxy. So this is more or less on the scale that you would actually measure. So the central core of the galaxy here goes out to a few kiloparsecs. Well, you may not remember, but our distance from the center of our galaxy is about 8 kiloparsecs. We're not in the center of the galaxy where things are interesting and exciting. It's like living in Saint-Genis. You know, we're out on the far distant regions where things aren't very exciting. So this would be the central core of M33, and it's very bright. There's a lot of stars there. But as you go out to 5 kiloparsec, the light starts to drop off, but the rotational velocity doesn't. This is a measure of the rotational velocity as a function of the distance from the center of M33. Now, if you would make the assumption, make a model that the rotational velocity is determined by the mass that you can see, so you use the surface brightness of the galaxy as a function of radius as an indication of the mass of the galaxy as a function of radius, what you would find is the rotational velocity would increase, but once you get to about this point, then there are many fewer stars out here, so you have sampled most of the mass, most of the luminous mass of the galaxy, and the rotational velocity as a function of radius would just follow Kepler's law, would decrease. But as you can see, that's not what's seen, and the discrepancy is not small. It's an enormous discrepancy. So this is the result for M33, and in fact, this result happens for rotational curves of just about all spiral galaxies. The flat rotation curves were discovered in the 1960s by Vera Rubin, who is a real, to my mind, a real hero in this game. She did some remarkable observations and had a remarkable life, becoming an astronomer in an age where there were essentially no women astronomers, and astronomy was even more chauvinistic than physics, if you could imagine such a thing. This is a compilation of the rotational curve, of rotational velocity as a function of radius, the rotation curve, for what's known as a whole bunch of galaxies, right? And this is put together by a combination of measurement methods. This is Sofue and Rubin's work in a recent review in Annual Reviews of Astronomy and Astrophysics. In the interior part of the galaxy, they use they measure the rotational velocity of CO. In the optical and disk part of the galaxy, in the disk part of the galaxy, they measure with optical, and in the outer part of the galaxy, where there's not many stars, they measure H1 lines, so they can measure the rotational velocity by H1. So you see that it's just not M33, it's just not our galaxy. All of the galaxies we look at have this form. And you notice that this goes out to 10 kiloparsecs or so, or maybe 15 kiloparsec. But there have been galaxies where the rotation curve is measured out to 30 kiloparsec, and some even a little bit farther. And we just don't see the Keplerian fall off in the rotation velocity. Most of the mass of the galaxy is not luminous, it's dark. Now, there is another way to determine dark matter, and that's through its effect on gravitational lensing. So let's imagine, let me give you an example of gravitational lensing, how it distorts the images of objects. So tonight, if you go out and buy a telescope and go out in the backyard and look at Saturn, you might see something that looks like this. If, however, you point your telescope at Saturn and see something that looks like this, you know that one of two things have happened. One, either you bought a very bad telescope and you should get your money back, or there is a black hole of mass, about the mass of the Earth, between us and Saturn. So if we put a black hole between the observer and the image, it will act like a gravitational lens and distort the image. And if we make careful measurements of how the image is distorted, we can deduce the mass of the gravitational lens. Even though the gravitational lens is unseen, we can deduce its mass. So gravitational lensing has been used as a way to deduce the mass of clusters of galaxies. This is an example, it's a little bit too bright in here to really see it well. This is an example of a picture made of a galaxy cluster by the Hubble Space Telescope. And these orange blobs are the foreground cluster of galaxies. You see the galaxies? And these wispy things here that form an arc are the distorted images of objects that are on the other side of the lens. So by measuring the distortion, how the gravitational lens distorts space, distorts the images of the objects behind them, we can deduce the mass of the gravitational lens, deduce the mass of the cluster. If, in fact, it is a point mass and for the gravitational lens, and the point mass is exactly on axis with the object behind, then what you would form would be something that's known as an Einstein ring, which would be a ring of infinite magnification, and you would measure essentially the radius of the ring. This is the formal result that obtains for a point-like lens and perfect alignment between the observer, the lens, and the object behind. So if you do not have perfect alignment, if the lens is not exactly a spherical mass point, does not have spherical symmetry, then it won't be a perfect circle. It will be broken up and the type of object that we see there, type of event that we see there. The mass deduced by this method agrees with the mass for the for the cluster, which is the lens, deduced by measuring the velocity dispersion of the various galaxies in the cluster. Just as measuring the rotational velocity of a spiral galaxy can be used to deduce the dynamical mass, measuring the velocity dispersion of galaxies in a cluster can be used to determine the mass. We can also determine a mass of a cluster of galaxies because there is gas in the cluster, and the gravitational potential of the cluster of galaxies are so deep that the gas is very hot, and it can be seen in X-rays. So using X-rays, using dynamical means, and using gravitational lensing, all these methods can be used to deduce the mass of a cluster of galaxies. And the mass that's deduced is much larger by factors of 500 or so than the mass you see in the form of bright luminous matter. So most of the clusters of galaxies are dark. Now, you can imagine, so you're using the clusters here just as a gravitational lens. You can imagine that, in fact, there are clumps of dark matter that are around that are not associated with clusters of galaxies. So this would also distort background images, and there's a project underway to try to build a telescope and measure the gravitational lensing by dark matter clumps that need not be associated with clusters. And this is a simulation, I'm sorry you can't see this down here, done by Tony Tyson, who can't hold a job. He used to work at Bell Labs, then he had worked at AT&T, now he works at Lucent. I guess he can't hold a job at a single place. So he's working at Lucent now, and in fact this would be a large region of the sky, and if there are dark matter clumps, what you would see is the effect of gravitational lensing, and by measuring the distortion of background images, very distant galaxies, you can determine the mass distribution. So this may be what the sky would look like if we look deeply, and this is a numerical simulation of what the sky looks like caused by gravitational lensing. There was also an artistic simulation of gravitational lensing that was done even before the time of Einstein. So in fact and you see the clusters of galaxies and the lensed images, and you can take the power spectrum of that and realize that Van Gogh knew about dark matter. Now, most of the matter is dark, and we believe that most of the dark matter cannot be baryons. And I discussed the results of primordial nucleosynthesis, that primordial nucleosynthesis is consistent if there's a baryon density today that's smaller than the density we deduce for dark matter. In addition to that theoretical argument, there's another theoretical argument that the dark matter cannot be baryons. And that argument comes from our idea of the formation of structure. And this is, I guess, a graph I believe I showed in the first lecture showing, or maybe the second lecture, showing the transfer function, the evolved power spectrum. If most of the mass is in cold dark matter, this would be the power spectrum. But if most of the mass is in the form of baryons, because of silk damping, the perturbations in the baryons will be wiped out. And the baryons undergo damped acoustic oscillations. So it does not provide any power on scales of galaxies and even up to the size of clusters of galaxies. This is another argument for dark matter. Okay, so most of the universe is dark. What could it be? There is this idea that's been floating around for years that goes by the name of modified Newtonian dynamics. And this is an approach or an idea that says, well, there's not really dark matter. What you're seeing somehow is modified Newtonian dynamics. That in limits of small accelerations, very large distance scales, the Newtonian physics breaks down, not at small scales, but at large scales. Is there any other evidence of modified Newtonian dynamics? I used to think there was no evidence, but since coming to Switzerland, I've learned, in fact, that there is evidence for modified Newtonian dynamics. Velocity equal mass times acceleration is modified Newtonian dynamics. And we have to take this seriously because it is a precision Swiss chronograph that made this. It's not even a watch. It's a chronograph. A chronometer. My daughter asked me the difference between a chronometer and a watch, and I told her it was about 1,000 Swiss francs. I think that's right. All right, so this is the only other evidence for modified Newtonian dynamics, so I won't speak about that anymore. Now, what about the possibility that the dark matter is in the form of baryons, but it's in the form of baryons somehow that's clumped together in things that we can't see? So in our galaxy, there could be a lot of planets that we couldn't see. Or there could be a lot of stars that used to be called dwarf stars. But now in the U.S., that's considered politically incorrect, and they are referred to as mass disadvantaged stars. If the star is very light, if it's mass disadvantaged, has a mass smaller than about 1/10 of a solar mass, or 1/2 of a solar mass, it will be very dim. It will also be light disadvantaged. And you've heard of white dwarfs, white mass disadvantaged stars, red ones and brown ones. They would be hard to see, just very, very dim stars. Another possibility, of course, would be black holes. We can't see black holes. Although we can't see these things directly, we can search for them through their effect of microlensing. Again, the fact that they distort the image of objects behind them. Now, these stars have sufficiently small mass, these mass disadvantaged stars, that the Einstein ring that's formed with the amplification would be on the angular scale of about a micro arcsecond. So we would not be able to resolve the Einstein ring But what we would see would be the effect that it would appear that the star would brighten if a dark object would, if a lens would pass in front of it. So there are projects that look in the Large Magellanic Cloud, that look toward the Large Magellanic Cloud. They don't actually go and look in the Large Magellanic Cloud. They look toward it. And the Large Magellanic Cloud is a nearby dwarf irregular galaxy that's about 150,000 light years away and contains about 100 million stars. So there's an observer, as a typical observer, looking at a star in the Large Magellanic Cloud. And if there's a brown dwarf that wanders in across the line of sight, it's going to cause gravitational lensing, but the observer does not have the resolution to resolve the Einstein ring around the brown dwarf. What he would see would be a change in the apparent brightness of the star, of the Large Magellanic Cloud star, as the brown dwarf traverses the line of sight. And this has been seen now, this effect has been seen of microlensing for a few years. This is just to show you how difficult this is. This is an example of one of the early microlensing events. So this is an image of a region of the Magellanic Cloud taken on day 387.6. I always think they should do it at night, but apparently they make this observation at day. So one of the great things about astronomy is that the interesting objects are always in the center of the photograph, right? Or the interesting objects have arrows pointing to them. That's another key in astronomy. You know, you look at the image, see where the arrows are, that's the interesting things. So if you look carefully at this star and compare its brightness to the nearby stars, you see that over days it becomes brighter. This was sort of a cloudy night. Let's ignore that. It gets brighter and brighter and brighter, and then it gets dimmer and dimmer and dimmer and goes back to the luminosity that it was before, to the magnitude that it was before. And this is an example. This is a graph, the quantitative picture of this. The amplitude of the light as a function of time, and it's in blue and in red. And this is the star that's being lensed. So this, you know, you're looking every night at millions of stars, little bitty things there, and you're looking for an increase in the amplitude over time. And this can be understood if there is a dim object that we can't see that's passing between us and the star in the Magellanic Cloud, and they also look toward the galactic bulge. The results of these series of observations have been going on now for about 7 years or so, maybe 8 years. And the evidence seems to be accumulating that most of the mass in our galaxy cannot be in the form of mass disadvantaged stars. There's just not enough microlensing events that are seen looking toward the Magellanic Clouds to understand the dark matter in our galaxy due to low mass objects. Something recently interesting has really come out of this. That is the fact that after a few years, they have seen microlensing events that are candidates for black holes. Now, if it's a fairly large mass lens, then the period over which the light increases and decreases is much longer. It would be on the order of year rather than a month for a normal brown dwarf. So this is an example of event. It's reported by 2 experiments, Bennett et al. And Mao et al. And Bennett et al. Report 10 microlensing events that are fit by larger than a solar mass lens. Now, if it's larger than a solar mass, they should be able to see the lens, but they don't see the lens, so it's not emitting light. It's too big to be a mass disadvantaged star. The possibilities that come to mind is that it could be a neutron star, or it could be a black hole. Chandrasekhar tells us that neutron stars cannot have a mass larger than about 2 solar masses. So if they see objects out here with masses this large, then they are candidates for black holes. Possibly these are black holes also, but these cannot be neutron stars. Down here they could, in fact, be neutron stars. So there's evidence now that there are black holes of about a solar mass in our galaxy. And I've become interested, in fact, in looking for nearby solar mass black holes. If you would think about how near a solar mass black hole could be to us, and we have not detected it, it could be just a couple of light years away, and we would not have detected it. Black holes are, well, pretty black, right? They're hard to see. So I'd like to indulge myself and talk a little bit about the results of a project I've been involved in with Jim Chisholm, my graduate student at Chicago, and Scott Dodaldson at Fermilab, looking for nearby black holes in a way that's not microlensing. So this is something that's holes in the hood. And we come to the conclusion that one of the objects here, and it's obvious which one it is if you think about it, could be a black hole. Well, black holes will accrete from the interstellar medium, and would emit radiation, and exactly what the spectral energy density would be, the energy emitted as a function of wavelength, depends upon the model, whether it's Ipsa-Price, advection-dominated accretion flow, convection-dominated accretion flow. There are different models for how a black hole converts the accretion energy of mass falling onto it from the interstellar medium into luminosity. And what we use are 2 projects, the Sloan Digital Sky Survey, which probes right here in wavelength, optical, and the ROSAT All-Sky Survey, which probes in X-ray to look for nearby black holes. So this is the closest I've ever come to astronomy, so I thought I'd spend 5 minutes telling you about it, because Fermilab in Chicago, along with some other very small liberal arts institutions on the East Coast, are involved in a project to map the sky, to build a 2.5-meter telescope and the instruments to image the sky, well, to 23rd magnitude, doesn't mean much to particle physicists, in 5 colors, which would produce about 1 billion objects, and take the spectrum of about 1 million of those objects that are extragalactic. This is a picture of where our telescope is, our observatory. It's in New Mexico. This is the 3.5-meter telescope. This is the 2.5-meter telescope that will be the telescope that takes the data we're going to use to look for black holes. Sort of an interesting design. You notice that there's lacking a dome over the telescope. We didn't forget about that, you know. But what we did was to design a telescope that doesn't have a dome, and when the weather's bad or we don't want to have the telescope outside, we turn it down this way, and this garage rolls over, the garage door opens, the garage rolls over the telescope, and the door closes. We once thought this would save money. This is in the background, for those of you who have been to New Mexico, this is White Sands National Monument. That's sand out there, that's desert. It's not clouds. There are no clouds at this observatory. They're not allowed. Also out here is Holloman Air Force Base, where B-2 bombers take off from New Mexico and fly wherever the United States happens to be bombing that time of year. The stealth bombers. And in fact, we had a project from the 3.5-meter telescope to shoot a laser up to the moon to do precision lunar ranging. And we were told we couldn't do it because there might be stealth bombers flying overhead. And we said, well, you know, we won't shoot the laser when the bomber's overhead. They said, well, you can't see them on radar. Then we said, aha, but we have infrared telescopes. We can see those planes with infrared telescopes. And we were informed that it is illegal to look at a stealth bomber with an infrared telescope. Okay, so this is the telescope, and this is the data acquisition system. Her name is Connie. And one of the instruments is very interesting. It's an enormous camera. This is Jim Gunn, the person who was most responsible for building this camera. And this camera, you know, there's silicon detectors here and particle physics experiments. For an astronomy experiment, this is a lot of silicon. It is 53 CCDs. 30 of them are 2K by 2K CCDs. And this is the schematic view of the camera with the 30 2K by 2K CCDs. And these CCDs have different coatings on them that are sensitive to different wavelengths of light. So they act as different filters. And you can imagine what happens just parking the telescope and having the sky drift across this in drift scan mode. So a star will be recorded here in this filter R, then go down and be recorded in I, U, can't read that, whatever, G, R. I forget what the alphabet is. This is alphabet soup associated with this. So we use this color information to try to separate the spectrum of stars from what the spectrum of black holes would look like. So there are, in the early data release, 3.7 million stars which have different colors. Most of them lie over here, but this yellow range is where we expect the black holes to be. So starting out with 3.7 million candidates, we can use the colors to reduce the 3.7 million objects to a possible 150,000 that are nearby black holes. So I told Jim, well, it's only 150,000 candidates. Why don't you look at each one individually to see if it's black holes? But that's not such a good idea. So you can also use another instrument, the results from the ROSAT Sky Survey, to see how many of these 150,000 objects are emitting X-rays, because we would expect if it is a nearby black hole, it should emit X-rays. That's the effective area or the sensitivity of ROSAT as a function of frequency. So all that's folded in, and what we discover is that out of the 150,000 candidates for black holes, 47 of them are also X-ray sources in possible black holes. 47 is a manageable number. In fact, 7 of them were targeted for spectroscopy with the result that there are 5 stars and 2 quasars. So we can form a catalog of possible nearby black holes and look at them individually, and we're in the process of doing that now. This is the picture I showed before, and there's one candidate here that looks very promising for a nearby black hole, a black hole that's only about 10 parsec away, and it's right there. I guess everybody could see that from the beginning. Okay, so I've spent a long time talking about the possibility that the dark matter is baryonic. Now I would like to turn to the possibility that the dark matter is non-baryonic. I talked about vacuum energy in the first lecture, and now let me turn to the possibility that the dark matter is some fossil remnant of the Big Bang, some elementary particle that was produced in the Big Bang. So the first candidate for particle dark matter was neutrinos. The only advantage for neutrinos is that neutrinos are known to exist. Admittedly, it's sort of a big advantage in looking for dark matter, but let's talk about the possibility that neutrinos could be the dark matter. Well, neutrinos are known to exist. Everybody knows that there is, in fact, a band, a rock group called the neutrinos. So neutrinos are known to exist. There are 3 active neutrinos and possibly stereoneutrinos. So in fact, when I look at this poster, I come to the conclusion that one of these guys must be sterile. There are 3 active and one possibly stereoneutrinos. Neutrinos are strongly suspected to have mass. In a couple of weeks, Alvaro Tarula is going to give a series of academic lectures on neutrino masses. You'll hear all about it. But there's evidence from oscillations that neutrinos have mass. And massive neutrinos would contribute to omega, contribute to the mass density of the universe. And the contribution of a neutrino of mass m nu, of a normal neutrino, not a stereoneutrino, is the mass of the neutrino divided by 90 electron volts. So a neutrino mass of a few electron volts would be very cosmologically interesting. A neutrino of mass 1 electron volt is still cosmologically interesting, and we should be able to see its effect in the power spectrum. In the second lecture, I talked about the evolution of the power spectrum and how the power spectrum changes from cold dark matter, why there's damping for hot dark matter like neutrinos, and if there is a combination of cold dark matter and hot dark matter, there is still a difference in the power spectrum. The Sloan Digital Sky Survey will measure the power spectrum to high accuracy, and this would be the effect, for instance, if it's a 0 mass neutrino, this would be the power spectrum. These wiggles here are oscillations in the baryon photon fluid that I've talked about. And you see the power spectrum is different if the neutrinos are massless and if the neutrino has a mass of 1 electron volt. These are model power spectra where the only thing that changes is the mass of the neutrino. It's also, and you can see that this curve and this curve are many sigma apart, so you would think it would be very easy to see the effect of a 1 eV neutrino mass. However, there are other things you can do to the power spectra by changing cosmological parameters, changing the baryon density, changing the tilt of the spectrum slightly away from the Harrison-Zeldovich result, or adding a cosmological constant, adding this or whatever, that can make this power spectrum with 0 neutrino mass look more like a neutrino mass of 1 electron volt. However, the people who did this analysis, Wayne Hu et al., looked at this and came to the conclusion that if there is a neutrino of mass larger than about 1 electron volt, possibly as small as a half of an electron volt, that Sloan should be able to see the effect of that neutrino in the power spectrum. So that's all I want to say about neutrinos, other than, in fact, neutrinos are very interesting to people at universities, no matter which department they're in. And the reason they're so interesting to people at universities comes from a paper that was written by John Learned, Sandeep Pakbasa, and Tom Weiler, 3 friends of mine, who talked about massive neutrinos. And down here, one of their conclusions are really startling if neutrinos have mass, is that relic tau neutrinos have sufficient energy density to close the university. So whenever I'm at the University of Chicago and my colleagues in other fields say, why do you care about neutrinos? I show them they can close the university. And suddenly they're very worried. All right, neutrinos are hot dark matter. Now let me talk about the most promising candidate for dark matter, and that is something that's known as a cold thermal relic. Cold, of course, refers to the fact that as the dark matter dominates the mass of the universe, it has a very small velocity. And it's thermal because it is assumed that at sufficiently high temperatures, at temperatures well above the mass of the particle, it is in thermal equilibrium. So you assume that at masses larger than the temperature, the relative abundance of the particle is about as abundant as any other type of particle. It's in thermal equilibrium. Now, if it would follow its equilibrium distribution, as the temperature of the universe drops below the mass of the particle, then its relative abundance, say compared to a massless particle, would be Boltzmann suppressed. So today, at 3 degrees Kelvin, if the mass is much larger than the equivalent of 3 degrees, then its abundance would be exponentially small. However, once its abundance becomes small, then there aren't many of them around to annihilate. And as the temperature drops below the mass, the number of particles that have enough energy in the thermal bath to pair produce the particle also becomes exponentially small. So what you would expect is that the particle would track its equilibrium abundance, but as the temperature drops and the abundance of the particle drops, it would freeze out from equilibrium. It would no longer annihilate because there aren't enough of them to find a partner, and they would not be created because there's not enough energy in the particles in the thermal bath. So the general feature is that it follows its equilibrium abundance, then it freezes out at some relative abundance, and where it freezes out determines its present contribution to omega. Now, the more strongly interacting the particle, the longer it's going to stay in equilibrium. And the longer it stays in equilibrium, the lower its freeze-out abundance will be. So the present contribution of a particle, of a cold thermal relic, decreases as the annihilation cross-section increases. So the weak inherit the universe. The more weakly interacting the dark matter particle is, the cold thermal relic, the larger its abundance today will be. So for the cold thermal relics, its contribution to omega today is proportional to a good approximation to 1 over its annihilation cross-section times the velocity. And these little brackets mean some sort of thermal average, because the particles have different distributions. They don't all have the same velocity. It does not depend directly upon the mass of the particle. It only depends on the mass of the particle insofar as the annihilation cross-section depends upon the mass of the particle. So if you know the annihilation cross-section, then you would know omega. Or if you say you know that omega in this cold dark matter particle is 0.3, 0.1, or something like that, then you can predict the annihilation cross-section. Now, if it annihilates to standard model particles like quarks and things like that, then what you do by knowing omega, you predict the annihilation cross-section. And then you can use crossing arguments to say, if I know the annihilation cross-section, then I know the scattering cross-section of the particle with quarks or neutrons or protons. And, of course, there's a lot of work that goes through this to get it right, but you can see that there should be some kind of relationship. If the annihilation cross-section is into standard model particles, it should have some scattering cross-section with standard model particles that is of the order of its annihilation cross-section. This was realized many years ago by Jeremy Goodman and Ed Witten, who pointed out that the annihilation cross-section needed to give omega equal to 1 suggests a scattering cross-section that, while small, even weaker than weak, but not many orders of magnitude weaker than weak, could be large enough that you can detect the relic particles today by its interactions with normal matter. And, in fact, that is the basic idea that goes into the detection of relic cold dark matter particles that are thermal relics. And the benchmark that people use the promising theory, that model that people employ, are supersymmetric models. And as you know, there's 105 or whatever numbers of parameters in supersymmetric models. So there's not one prediction for the annihilation cross-section or the mass of supersymmetric particles, but there are many. There's a parameter space of predictions, and there is also, for every model, a cross-section for the scattering of the dark matter particle, the relic dark matter particle with nuclei. So this is the predictions in some model, some realization of supersymmetric models. And this is the result of 3 experiments that look for dark matter by its present scattering. There's the Dama result that sees a signal here, certain cross-section and a certain WIMP mass. And there are other experiments, CDMS and Edelweiss, that have published upper limits, and the upper limits seem to sort of disagree with the results of Dama. But the experiments are getting better. There'll be some definite results soon. This is a simplified version, and you can find various complications of this in the constrained minimal supersymmetric model. These are sort of magic words that are said to produce models. If you ever seen the play Macbeth, you know, the witches are saying magic words, putting in eyes of newt, dog tongue, and things like that. These are the magic words said by people who build supersymmetry model, and there are various parameters that either you're familiar with or you don't care about, scalar masses, gaugino masses, etc. And you can predict in this plane here where you would expect to find supersymmetric dark matter. And there are many groups who do this. And you can examine these particular points in model space and see what the scattering cross-section would be on protons or nuclei. And these are the various models, and these are the expected limits in the next generation of experiments. So the idea that the dark matter is a cold thermal relic is testable, because if its annihilation cross-section sets its present abundance, it should have some scattering cross-section with normal matter. And if you're sufficiently aggressive, you can go out and look for it. There is a limit to the mass of a thermal cold dark relic particle. The annihilation, the present abundance contribution to omega depends upon 1 over the annihilation cross-section. And to get omega equal to 1, the annihilation strength is comparable to the electroweak scale. And again, the annihilation strength sets the interaction strength. But there's a limit to how large the annihilation cross-section can be. There's the unitarity limit that the annihilation cross-section must be smaller than 8 pi over mx squared. So in order to have omega smaller than 1, the mass of the particle has to be smaller than 200 TeV. Otherwise, its annihilation cross-section would be too small, and its contribution to omega would be too large. So for a thermal WIMP, the annihilation strength is determined, but the mass is undetermined, but has to be smaller than 200 TeV. So that's the result for thermal relics. Now let me mention the possibility that the dark matter, if it is a relic particle, may be non-thermal. And the idea of a non-thermal relic is somehow the present abundance of the particle is not determined by thermal processes. It's not produced by thermal processes. Because when it's produced, the equilibrium abundance of the particle is very small. A possibility for producing non-thermal relics is that the dark matter could be produced by the same mechanism that produces the density perturbations, the alarming phenomenon of particle creation in the early universe. The fact that the expanding universe leads to particle creation was studied a lot during the 70s and 80s, and the application of this that I talked about yesterday was the production of density perturbations from inflation and gravitational waves from inflation. Now there's a new application of this idea that in fact the expanding universe creating particles could create dark matter. In order for this to occur, there are three requirements necessary. You're going to require that there be some supermassive particle, called the dark matter is some supermassive particle. I'll define exactly how super it is. The particle has to be stable, or at least long-lived. It has to have a lifetime longer than the age of the universe. And the cosmological background has to be such that it's an initial inflationary era followed by the transition to a matter or radiation-dominated era. Two groups have calculated what the present contribution to omega would be as a function of the mass of the particle divided by the mass of the inflaton field driving inflation. Now, let me show you how a cosmologist reads this graph. Any number between 10 to the minus 3 and 10 is equal to 1. Any number between 10 to the minus 2 and 10 to the plus 2 is equal to 1. So looking at this graph as a cosmologist, you come to the conclusion that omega is equal to 1. In other words, you would have a dark matter candidate if the mass of the particle divided by the inflaton mass is of order 1. And the inflaton mass is somewhere, presumably, between 10 to the 10 and 10 to the 15 GeV. Oops, this is the same graph, sorry. Now, do we expect such massive particles to exist? Well, the inflaton mass, which is in principle measurable from the gravitational wave background, and we might guess 10 to the 12 GeV, since there are no measurements, I can say I know what it is on the basis of pure thought, may signal a new mass scale in nature. It could be that the inflaton mass is the only particle that has a mass of 10 to the 12 GeV. But what we've learned before about physics is once we find particles of one mass, then it's some mass scale, and there are other particles of that mass. So other particles may exist with mass comparable to the inflaton mass, and it may be stable. So this super heavy particle has been called a WIMPzilla because it's very big. And its characteristics are that it's supermassive. There are models that have them anywhere between 10 to the 9 and 10 to the 19 GeV. A narrow 10 order of magnitude window. So we tell the experimentalists, go look for something, the mass is somewhere in this range with 10 orders of magnitude. We don't want to pin them down too much. The abundance of the particle depends only upon the mass and not upon the interaction. So they may be completely sterile, or they may be electrically charged, have strong interactions or weak interactions, or they may in fact be unstable as long as its lifetime is larger than the age of the universe. What would the footprint of the WIMPzillas be? These honking big suckers around, how would you know? Well, if it's completely sterile, it wouldn't have any footprint. But they could decay, annihilate, they could produce isocurvature perturbations, or you may be able to have direct detection. So a question that comes up, is the dark matter a WIMP? Here illustrated by this picture of John Ellis. Or is the dark matter a WIMPzilla? The WIMPzilla is an example of a non-thermal relic. Another non-thermal relic is the axion. And time is getting short, and I don't remember what any of these transparencies mean. But people are out, everybody knows what an axion is. People are out looking for axions. If they had discovered them, you would have heard about it. So the review of particle dark matter candidates include massive neutrinos, which would be hot dark matter. Stereoneutrinos decouple earlier, they're not damped as much, or gravitinos are examples of warm dark matter. I guess there should be warm and fuzzy dark matter that you feel good about, and I haven't figured out how to do that. And then there's cold dark matter models like neutralinos, axions, axion clusters, WIMPzillas. And also, there may not be a true elementary particle. The dark matter may be a soliton. And there are B-balls, Q-balls, odd balls. People are working on papers like that. So that's what I have to say about dark matter. It doesn't, in 1 hour, I can't completely cover the subject. But let me step back now and remind you of what the goal of these series of lectures would be. It is to understand the origin of structure in the universe. Now, the origin of structure is a complex natural phenomenon. Look in the universe. See the variety of structures in the universe: galaxies, clusters, filaments, superclusters. This simple idea of gravitational instability, of the perturbations from inflation, is a simple, elegant, compelling explanation for this complex natural phenomenon. So it's a very attractive, appealing idea. However, we should keep in mind something that was said by Tommy Gold, who said, for every complex natural phenomenon, there is a simple, elegant, compelling, wrong explanation. And although this is the most promising explanation we have for the origin of structure, it is remarkably predictive and being tested by experiments and observations. We have to keep in mind that it may not in fact be right, and we shouldn't be deluded by the fact that it is simple, elegant, and compelling. So I'll give you the good news and the bad news in conclusion about what we know about the universe today. And let's keep in mind a comment that was made by the American philosopher Will Rogers, who said, "It ain't what you don't know, it's what you know that ain't so. That's the problem." So we have to keep in mind that some of these things that we think we know may not be so. So what do we know today? We know that the matter density of the universe is dominated by cold dark matter. The perturbations that lead to structure arise from inflationary dynamics, which depends on particle physics at high energies. And the universe today is dominated by a cosmological term. Sometimes it's called dark energy, funny energy. A name that's been given to it that's horrible is quintessence. Galileo wrote about quintessence, and Galileo said, I don't care whether you call it quintessence or polenta, it doesn't exist. Sometimes it's called a cosmological constant. I've argued that a better name for it is a cosmo-illogical constant. Well, this is a triumph. It's a great advance. These are things that we know. This is the good news. The bad news is we know nothing about the nature of cold dark matter. We know nothing about the dynamics of particle physics at very high energy, the dynamics of inflation. And we know less than nothing about the cosmological constant. So I hope in these lectures I've given you a flavor of the excitement and what we do know and why I'm glad the lectures are over so I can go back and try to learn something about what we do know. Thank you very much.